So I didn't knew the topics of the previous presentation. So I thought of this lesson to be a more general one. So I'll just skip the first part of the presentation to avoid to be redundant and too heavy. But just to give you some structure of this lesson, I wanted to talk about a brief introduction of what is an AI, what is why it is so popular nowadays, and after that, I want to give you some details about the architecture, the main architecture out there, about artificial intelligence. I will focus in this lesson about deep neural networks. So I'll touch also some machine learning, but I'll just talk about deep neural networks because they are very good about with mechanical properties prediction. So that's the main focus of this lesson. And after a brief introduction of this neural networks, I'll give you 3 examples that we have developed in ERC project about the prediction of static mechanical behavior of metallic materials, the generation of selected laser melting struct for accurate fatigue-resistant lattice design, and some modeling and optimization of static mechanical properties of fusion deposition modeling manufacture specimen. So about the first part. I think now you know what is an AI after 2 hours of presentation, so I'll just skip this section. AI nowadays, the most famous AI nowadays are that I'm sure that you're using it are ChatGPT, DALL-E. Now DALL-E 2 doesn't exist anymore. There is a DALL-E 3, Sora, and Midjourney. The first one is general language model. The other 2 are text-to-image models, but they are essentially artificial intelligence, very deep artificial intelligence. But why AI is so much important nowadays? Because it's very deep rooted in our socio-economical environment. For example, nowadays AI are used daily to do weather forecasting. I don't know if you have noticed, but the more time passes, the more weather forecasts are really more accurate than in the past. And this happened since AI now are used instead of partial differential equation. So since we are using artificial intelligence now trained on real data, we are achieving much faster and much accurate weather forecasting. Another application that nowadays AIs are used to is the prediction of stock markets values. And I knew some friends that works on that, and this is a real application. And a lot of people just jumped into AI to do that because this can generate revenue because you predict the stock market and you can exploit that prediction. And another application that a lot of people, I think here, all of the people use daily is the classification of the face and of the fingerprint to unlock their phone. So that's really small, but it's technically neural networks on your phone that it just classify your face and your finger, and it will unlock your phone if it's you. So as the previous speaker said, neural networks and artificial intelligence aren't really a new topic. They were born in the past, and one of the first application of artificial intelligence and neural networks is the multi-eye perception. The multi-eye perception, it was a very, very simple network because it approximated somehow the inner structure of the human brain. And if you decompose the problem into very small unit, essentially the neural behavior of the behavior of neurons in our brains can be decomposed into 2 mathematical operations. The first one is a linear operation. So if we think about neurons and the dendrites, in which the electric signals comes to, once a signal arrives into the neuron, we have a ion that is traveling towards the neuron. So we have a linear increase. We could approximate it as a linear increase of electric potential. So essentially, we have a linear slope. And after a while, after we reach a value, the neurons fires towards another neurons. So that activation function can be approximated as a step function or in a much more continuous way as a sigma function. So by combining this very simple mathematical operation, we are basically approximating very roughly, but we are approximating the functioning of a neuron. So extend data by a lot of neurons in parallel and with a lot of layers of neurons, and we have basically created a multi-layer perception. About the optimization, I will skip this part because you had just a lesson about it, but I want to just say that neural networks are becoming a reality just now because in the past years, you were just constrained with a CPU-based operation. And since you have to optimize all those weights, that procedure was costly, and most of all, it was very time-consuming. But since now, thanks to gaming, strangely, but thanks to gaming, we have some graphic cards. We can parallelize a lot of those very simple operations because we are talking about summation, some products, some other operations, but they are very simple. They do not require that much computational power that a GPU offers. So you can parallelize those operations on the graphical cards, and you achieve a lot of speed up, about 3 orders of magnitude. So that's why artificial intelligence is becoming a thing just now. Now, the introduction has been done, so I'll talk very briefly about some kind of architectures, because this is the architecture I've used in the next section. So it's useful to me to just introduce them a little bit. So as I said, the multi-layer perception is a very simple structure. I mean, isn't technical multi-layer perception because in this case the activation function isn't a step function, is a user-defined, but is a multi-layer perception-like structure. It's a very simple structure in which each layer of neurons is fully connected to the previous layer. Okay, so it's a fully connected network, and it's maybe the most simple kind of neural network that you can have, but despite its simplicity, can very easily learn complex structure into data. And most of all, it can be customized very easily, and you can develop ad hoc structure for your task. So for example, here, there is a neural network called, a neural architecture called N-bits, in which you basically create N blocks based on the multi-layer perception architecture, and you force each block to map into a kernel. So for example, Taylor kernel, or a Fourier kernel, or just a linear kernel, and you can decompose your data into a trend, a cyclic part, a residual part. And this is really useful because, for example, here with this net, you can somehow predict weather, you can predict stock market, you can predict some data that manifest this kind of structure inside itself. So this is why multi-layer perception are really good, and they're used a lot, because if you modify them a little bit, you can essentially fit it to your data very easily. So another kind of neural network that I want to talk about, but very, very briefly, just to prove a point, is the convolutional neural networks. Because the convolutional neural networks, aside from the mathematical point of view, they were born once we understood how our brain worked images. Because when you process an image, your neurons aren't looking at the whole visual, at the whole image that you're seeing. They look at just a portion of it. So they look at that portion, and after a while at that portion, and after a while at that portion. You have not all your neurons focusing on all the part of your image. And basically the convolutional networks just do that, and they work because of that, aside from the mathematical point of view. So as the previous lesson was focused about, you have a kernel that is applied to the image, that it compresses the image in a more meaningful representation. But the beauty of this kernel is that if you stack different kernel, your neurons extract different kind of information. So you can extract, for example, edges, you can extract gradient of color, you can extract textures. And that's the beauty, because each kernel essentially specializes onto a different thing. And at each pass, you're compressing the information even more. So once you have extracted the information, you can basically just attach a multi-layer perception, because the information about the image has been extracted. So you need a neural networks that somehow maps that extracted data and that learn the information contained into the data. And multi-layer perception are very good at doing that. So by combining those two architecture, you have created essentially the famous Laurenti or any other convolutional neural networks that use this kind of attachment. And for example, convolutional neural networks are very used nowadays to do segmentation. For example, the online segmentation that are used in a lot of autonomous driven cars, such as Tesla, but nowadays a lot of other cars. They're used also in airport to classify malicious malicious people. They classify by movement, by behavior. So they are very used nowadays, this kind of neural networks. Another kind of really interesting neural networks that will be see a lot in our work are the recurrent neural networks. Recurrent neural networks, they process sequences, and they work basically also as our brain works. But why sequences are so much important? Here you see a very simple GIF. You see a speeding car. But here, there are no information about the speed of the car, but by observing the sequence of image, you can tell that this car is very fast indeed. You will agree about that. So we extract contextual information about what we see, what we experience, by correlating a sequence of not independent data. And that can be somehow exploited to learn some meaningful patterns into data. For example, for weather forecasting. In weather forecasting, of course, the previous observation isn't uncorrelated with the subsequent observation. For example, if yesterday it was 20 degrees Celsius and it was sunny, tomorrow possibly it will be 21 maybe degrees, or 19 if you're approaching the winter, but it will not be minus 40. It will not be 80 degrees. So each observation are correlated to each other. And that's not just constrained to weather forecasting, but it's also true for the mechanical behavior of materials. For example, if I pull a specimen, the mechanical behavior is really correlated with the past instant. And for example, here, after it undergoes the elastic limits, it started the plastic deformation of the materials. So by also providing the neural networks those sequence information, you can learn the mechanical behavior of your material itself. So about the recurrent neural networks, their functioning is very, very simple. They are based on memory, so you have to somehow pass some information through it. The most simple kind of recurrent neural networks, it just use the past prediction, but or the past observation, but honestly isn't really used nowadays. You use normally the long short term memory of the gated recurrent unit. I won't go into details, but essentially by doing some mathematical operation inside of it, they retain some memory, some long or some short kind of memory. But they can memorize pattern, different kind of pattern inside your data. And those kind of operation, funny enough, are the same kind of neural operation that are inside of our brain. But that story is on the contrary, respect of the convolutional networks, because the biological discovery was done afterwards, the recurrent neural networks. So that's why they work, because they just mimic nature without knowing, but they just mimic nature. So that's for recurrent neural networks. The last kind of architecture I will show you, and after I will jump to the application, is the transformer. The transformer is maybe one of the most widely used OBI nowadays, since each one of you use ChatGPT, Gemini, or maybe also some text-to-image tools. That's basically a transformer in it's a stealthy transformer. So you don't see it, but it's essentially a transformer. A transformer is a very simple net, honestly. It's very deep when you use it with a ChatGPT or a Gemini, but essentially this is the simple structure of a transformer. And okay, and the way they works is really simple, but before diving into how they work, I have to focus a little bit on how do you encode words into numbers, because with a regression is really simple. You have to predict a value, but a value that is itself a number. You're trying to predict temperature, you're trying to predict maybe strain or stress. That's a number. So you have to just predict another number. When you're using images, an image is just an array of numbers. If you have more channel, they are just a multi-dimensional matrix, but they're just numbers in the beginning. So how do you encode a word that is not a number into a number? You use something, there are also other kind of algorithm, but you use essentially a one-hot encoding. So you assign a token to your word, a token that can be anything. So 1, 2, n, as n is the length of your vocabulary. You essentially encode that word to be a vector, an n-dimensional vector that is 0 everywhere, but in the position of your token. So for example, here, the word apple is the 4th token. So if you see here, the encoded vector is 0 in every position but the 4th. Okay, so it's a very simple kind of encoding. But why I'm doing that? Because I'm exploiting one very nice behavior of neural networks. Neural networks can learn and can optimize their weight. So if I project this vector into an n-dimensional latent space, and I can use neural networks to do that, and I optimize the neural networks to give me good prediction, I am implicitly asking to optimize the latent representation of the words in an n-dimensional latent space. So essentially, the neural network itself will find similarity between words. And that's really neat. And that's how transformers works. So they don't know about our vocabulary, about our rules of grammar, but by being trained on text data, they can extract similarity between words. Because, for example, I will use a lot the cat words with a cute, with a feline, with animals. So it will learn that somehow cat is related to an animal, is related to a feline, is related to the concept of a cuteness somehow. Okay, so that's how this kind of neural networks work. And they are not just as simple as that, because as you know, word phrases has a different cluster. What does that mean? When you say a phrase, you can have a different section of your phrase. So maybe some words that you say at the beginning relates to something that it's at the end or at the middle. So you need somehow to enforce a kind of attention, a kind of local clustering into your neural networks. And the main components of a transformer is the attention mechanism. So essentially, it can learn it can learn how to make the networks to be attentive towards certain words. Okay, so for example, here you will have just the short relationship between words. Here you will have the long relationship between words, and that's what the attention mechanism does. And as with the kernel, you can have n attention mechanism. So each attention mechanism will focus on a particular kind of relationship. For example, here, the short period or the long period relationship. So as for transformer, aside from the large language models, you find the most famous application of those models in true translators. Google Translate, DeepL are just transformers, or in this case, encoder, decoder, but they use essentially the same logic. So you encode your initial phrase in one language, and after compressing it into a Latin space, you decode it into the target language, and you'll have your nice translation. Okay, so that's for the kind of architecture. It was kind of necessary to somehow introduce those concepts because they are heavily used in the next section. So the first research, it's really small, but it's important for the next one. So the first research I want to talk about is the prediction of the statical mechanical behavior of metallic materials. And when I'm talking about mechanical behavior, I'm not just saying, okay, predict me the yield stress, the UTS, or the fracture stress. That's not the mechanical behavior. Those are the mechanical properties. When I'm saying the mechanical behavior, I want the whole strain stress curve. Okay, and I want to also have a network that learns the plastic deformation, that learns the hardening of the materials, that learns maybe how these curves change while varying the manufacturing parameters, the testing parameters, the testing condition, the strain rate, the temperature. Okay, I want something like that. And nowadays, there have been some research that have used recurrent neural networks to do that. Because, as I said before, recurrent neural networks use sequences. And since this technically is a sequence, it can learn the relationship inside of it. And what's nice is that neural networks are really fast. I'm talking about milliseconds fast. So you can use data also inside a FEM subroutine. Because, for example, we are trying to optimize, I don't know, something. And by doing a subroutine that they use neural network under the hood, you can speed up your computation. Or you can do some custom, maybe a design. So in this research, I have combined different neural networks, and each neural network, each layer does different things. So, for example, the first layer is the long-short term memory. The long-short term memory, it extracts data from the input sequence. So it essentially, extracts information from the sequence. The CFC layer technically is also a recurrent neural network, but it's a very special kind of neural network. It's very new. I haven't seen, honestly, any research using that, but I think it's a shame because it's really, really powerful as a layer, because it does, under the hood, an approximation of an ordinary differential equation. So here, technically, it correlates temporally the data extracted from the sequence. And that's really important because We will see it later, but that was a limitation of the long short-term memory, because the long short-term memory cannot extract time. It cannot extract a time relationship, but the CFC layer can allow that. And also here it's used also a multi-head attention in the whole sequence to extract data in the sequence itself, for example, going backwards. Maybe this point, the yield point is important, maybe, in the sequence. So maybe it needs more attention to it. So that's the catch about the multi-head attention. So about the CFC layer, I want to go a little bit in deep about that, because as I said before, as I shown before, neural networks aren't just mathematical operation. Yeah, they are mathematical operation, but they are heavily bio-inspired, okay? And they work because they are bio-inspired. So in this case, CFC block are connected, of course, but with a sparse connection. So there is not a fully connected networks. And that's really useful because, if you observe in deep what it's happening in neural networks, you see that during the training, a lot of weeks are changed, but sometimes if your neurons are too much, they are zeroed during your training. And okay, they are zeroed, but that process can cause some numerical instabilities inside the guarded descent algorithm. So you can go towards a not optimal solution of weight. So you will have essentially a lower accuracy. So through enforcing some scattered synapses, but with a scattering that has been bio-inspired by the structure of the C. elegans, that is a nematode, you will have an increase in prediction. So, for example, in this case, you'll have the hidden layer that will be decomposed into three sub-vector, and those vector they will go into three different layer of CFC block. Those blocks are the interneurons, the command neurons, and the motor neurons that are present into the C. elegans. Now, it has been chosen, the C. elegans, as the organism to be inspired towards it, because those nematodes is very capable of exploring its environment, of mating, of surviving, despite having just 128 neurons. So its neuron structure is heavily optimized. So its connections are very good. So this is how the wirings has been performed. And honestly, the command neurons are also full of a recurrent connection. So there are also some parallel information carried. And after this CFC block and the multi-head attention, the decoder is just a multi-layer perception. So about the temporal correlation problem, I want to stress this point, because that's really why this architecture has been deployed. Normally, recurrent neural network, and if you train on normal data, you won't have this problem, but it can become very easily a problem. So normally, recurrent neural networks expect equally spaced data, because maybe you are training your data with some sensor, and normally sensor, they sample data with a given frequency, 10 hertz, 600 hertz, you decide that. And you have no problem by feeding that data with recurrent neural networks, because the temporal data are equally spaced. But what happens if you have a different sensor with a different sample frequency? Or the worse, what happens when you have you're doing a test, and those tests have different sampling rates? For example, during a fatigue test, during a creep test. During a creep test, nowadays, the very good machines have different sampling rates that the triggers depending on the region that you are during the creep, to have a less heavy file in the end. But those data are very good for us engineers, but they are not very good for recurrent neural networks because they cannot tolerate a broken time symmetry. And for example, here there are some results when you try to train neural networks on data that have a broken time symmetry. You can see that the predictions are not good. They are not really good. And here it didn't even learn the mechanical behavior. They just replicated the trained data. Because, for example, here we have a mono-loading path. Here we have a multiple loading paths with some discharge. But here, for example, with a long short-term memory, it doesn't even know that it doesn't have to go to 0. So it just follows the training data. And that's a problem, because that's a really simple toy data set. But if you try to implement this with a lot of sensor, with a lot of data, you have basically unreliable prediction. But with using the CFC layer, so allowing an approximation of the ordinary differential equation, you essentially correlate time, you use time in your data. And the prediction, the data set was the same here and here. But see here how the predictions are completely fine. And here, for example, there are some prediction done on an aluminum specimen. It was not really a really particular aluminum specimen, but as you can see here, the training data is the blue one, and the orange one is the prediction. And mind that I asked him here to predict me just a static load, so without any unloading, just a complete loading. As you can see here, it predicted me very well the elastic behavior, the hardening, and also the damage, because here it was starting to decrease. And also here, while imposing a different unloading path, it also predicted me very well a different unloading path. So essentially, the neural network was able to learn the real behavior of the materials. For example, here, another, I have plenty of those images, but another application, it was done on an easy 360L specimen, manufactured at the same condition, but tested at different temperature and different strain rates. And those are testing partitions. So this is data not seen by the model. And as you can see here, the predictions are really good. It's basically a perfect prediction. Yeah, the curves are really are unusual in form, but it's just for the size of the image, because if you make it rectangular, they are very similar to this one. Okay, I say that because that's a question that normally it's asked to me. And those are other applications of these neural networks. For example, here it was on steel, spring grade steel. At a very high temperature, so there was some creep involved here. Here it's some aluminum. I don't quite remember because it was 3 years ago, but it was some alloys of aluminum formed with different techniques, and it was able to predict perfectly the different forming, how it does affected the mechanical behavior of the materials. And also here, there was dependence on the temperature of testing. And here, it is the prediction of a additive manufactured specimen printed at the different angles. And what's nice is that here, it gives you also the confidence interval of your of prediction, because the thing is, neural networks can be really customizable. Here, the decoder, so once you compress all your sequence information into a latent space, you decode your information to just give you one prediction, and you can use just one decoder. But what if you use two decoders? because maybe you think that your data is distributed not with a deterministic distribution, so not with a delta of Dirac distribution, but for example, to a Gaussian distribution. You can have two heads, one modeling the mean of your distribution, one modeling the variance of your distribution. You can apply a different loss function. So for example, a negative loss likelihood loss function, of course, mapped for the Gaussian distribution. And you get here prediction for the also for the variation that your data could have. So we have, for example, a confidence region here. You cannot see it because it's very small, but maybe here you can see it. Here there are some spikes on your prediction, and this is because technically sometimes in the data after the loading there was some spike. So there is the value that possibly the model could reach statistically. So that's the first research I wanted to show you. The second one is really big. It's really, really big, and it's based on the results of the first research. Because as Professor Berto said, we are trying to manufacture some materials, some structure that are very resistant to fatigue. And one of the most promising structure are the lattice structure, because they are very efficient into the ratio of mechanical properties versus density of them. But they have a very huge problem, if I can say so, is that the topology that we design in our CAD software is very, very different from the topology that we encounter after we print the piece. Because of course, we will have a lot of roughness, a lot of defects inside the specimen itself. For example, some lack of fusion regions. And those defects, those roughness, change the mechanical behavior of your lattice structure. And that's a problem for static behavior, but not a huge problem, because you will see some deviation from the from your design prediction, but it's not a too much of a big deal. But for fatigue, roughness is really crucial, because if you design a structure to fail at a certain number of cycles with a given load, it will give you completely different behavior once you manufacture it, because it's full of ridges, it's full of bumps, it's full of defects. So you'll have a great difference from your design lattice and your manufacture lattice. And that's a problem. That breaks the whole optimization process. So what we wanted to have was a tool, an AI, to artificially generate those topologies to be able to apply them preventively to the designed lattice. So for example, if I print a strut at 45 degrees, I have this kind of topology, I stick it to the generated into the CAD. I stick it into the CAD to the my design lattice. I test it with a FEM simulation, and I will have a much more high fidelity prediction than the normal one. Because right now you could do that, but you can just have the topology once you have printed the materials. So that's not really that much useful, because you have to design every time your lattice, so you can do a very fast topology optimization, because each time you have to manufacture your pieces, so it isn't really that fast. So we have to use a generative AI. Generative AI is a little bit different from what we have seen right now with the previous presentation, because it's neither supervision machine learning, neither is unsupervised machine learning. Is something in the middle, because technically it's playing a game with itself. One of the most famous kind of generative AI, it was the generative adversarial network, where there were two neural networks. One, it was the generator. One, it was the discriminator. The generator was generating fake images, and the discriminator had to discriminate if that image was fake or it was true. And they were playing a game against each other. And by playing that game, by optimizing their ways during the training, they were capable of, at the end of it, the generator was capable at the end of generating very, very good quality images. Those are not real people, but they seem very real. And so basically, the whole pipeline here is based on this slide. So we had to, at first, extract the topology of our strat. We could use CT scanner, of course. A CT scanner, they call the standard for topology acquisition, but we wanted to create something cheaper. So we just used stereo optical images. We extracted the contour of the stereo optical images. And so by assuming that the struct was cylindrical and the struct technically was cylindrical, we had assumed that the struct geometry with defect was an ellipsoid, and we essentially extracted the coordinates, the defining coordinate of those ellipsoids. So here we have I don't know if you can see it, but we have the upper skin, the lower skin, the left skin, the right skin, and the coordinates of the centroids. Okay, and those coordinates define the topology of the struct under the assumption that it's an ellipsoid. And so what we were trying to do is, after the generation of this spline, we have to create a statistical database. We have to reconstruct the mesh of the strat, and we have to simulate with ANSYS to extract, to do essentially the SED analysis, to extract the most critical points. But that was a problem, the statistical database, because technically, if we use a standard random generation, maybe we see that the distribution technically of the semi-axis and of the centroids adheres to the Gaussian distribution. So we could think about sampling by those distribution. If we reconstruct a struct with this logic, you can see that the reconstructed strat isn't really similar to the real one. You can see it, that it has some very big problem. For example, here there is an abnormal friction. So technically, this is something that you cannot see in the reality. So if you use this struct for the topology optimization, you will have a different kind of problem, because you will have a very wrong prediction, but wrong for the wrong reason. Okay. So this, in the end, will lead to invalid assumption. So what was our approach? We had to somehow use AI to generate those topology. And the pipeline now, it becomes that. And I'll go into details of each step. So technically, we are trying to learn this kind of distribution. Okay, so we want to learn the distribution of trajectories associated with the struct, and this is something similar to the generation of fake images. It's similar, but it's not the same, because here we are dealing with sequence. So there wasn't very much literature about it, honestly. So we had to improvise a little bit. Those are three kinds of architecture that we tried. The first one is the autoencoder. This was maybe the first kind of generator that it was ever developed, because it essentially is trained into doing an autoregression. So here enter X, and it has to give X. Okay, very simple. But why you do that? Because after training, you just take the decoder, you sample from the latent space, and technically you can generate images. But it has a problem. It only gives you blurry outputs. So it was abandoned towards the generative adversarial networks that I've shown you before. But generative adversarial networks itself, they have a lot of problems, and one of them is the instability of their training, because they can collapse. For example, they can collapse towards just one distribution. For example, you're trying to generate images of real people, they just collapse to images of blonde people. If you try to sample from the GAN, it only gives you images of blonde people, and that can be a problem, because, for example, in this case, it could collapse into just one kind of topology. But with the images, we could somehow see that there was a problem. With sequence, not very much, because it's very much complicated. So we wanted to use something very new. There is basically no literature about it, just one study with the non-adversarial networks. This is essentially a decoder-only architecture. It is something very similar to ChatGPT. ChatGPT is a decoder-only network. Okay, so it's very easy to train. It doesn't suffer from mode collapse like the GAN, and it's simple as the autoencoder to train, but it gives you very, very good sample. So here you have a problem, because I'm trying to generate something. I have to encode the data, the struct data, into numbers. How do I do it? If I consider if each slice of the struct as a word, as an entity, I can encode each slice of each struct with the one-hot encoding logic that I've shown you before with the transformer. And I want to do that because I want to learn the best possible latent space associated with that kind of domain, the domain of the struct slices. So in this case, without providing any information, the neural network itself was able to learn the data structure. But we have a problem here, because a problem that we didn't have with the transformer, because technically we want our latent space to have some very nice properties. For example, this is a completely unrelated task. I am encoding the square shape into the number 1 into my latent space, okay? And I've encoded my circle shape in the number 4. If I move from square to circle, I want to see something like that. I want to see the square morph each time that I move closely to the 4 into a circle. I want to see that because it's logical. My latent space should give this kind of transformation, okay? But in reality, when I use that kind of encoding that it's popular with transformer, if I go towards a number to another, I have some gibberish words, okay? And that's not a problem with transformer, because I'm not trying to create new words. I have those words, I stick to those words, but it is a problem in my case, because once I train my model, I want to explore the latent space to generate a different kind of struct, okay? So this is a problem that needs a fix. So normally, if you observe latent space, if you somehow can project latent space into 2 dimensions so you can see them a little bit, though the shapes isn't really nice, is a lot like this, but honestly it's so much worse. It's full of peaks, full of valley. It's morphing very, very strangely, so it's very unstable. You want a latent space that is smooth. So the variation autoencoder, for example, tried to solve that issue by imposing that the latent space was curved like a Gaussian ball, but it doesn't need to be like that, because it needs to be smooth, but not that smooth, okay? And in our case, we smoothed the latent space by constraining the embedding space with this L2 norm. So essentially, I was asking the model, okay, so give me a representation where if I vary a little bit the embeddings, the loss function doesn't vary that much, okay? And by doing that, I mean, those are just references. This is not the real latent space, but by doing that, the latent space now, it was a lot smoother. So I had essentially regularized my latent space, and the network itself now, it worked. So about the structure of the neural network used for the generation is, as I said, a decoder only. So it's essentially as a decoder, as an autoencoder, but without the encoder. The network itself, since here we are processing sequences, we are using the same architecture that I've shown you before. So the LSTM, CFC, multi-attention. Okay, so we have this block that continues to appear because it works. Okay, because it works really good with every sequence. So one thing that is really nice about artificial intelligence is that if something works into a dominium, and you have a dominium that is similar, you can apply this in neural networks. For example, sequence. You can apply it to weather, you can apply it to mechanical behavior, you can apply it to topology because they are always sequence. Okay, neural networks are not affected by different dominium if they are similar enough. Okay, so here we have now a problem. We have to cluster data because they didn't tell me, but apparently there were different kind of specimen inside of these datasets. And I catched that because the network itself wasn't converging. So I had no idea how to classify them because they were printed onto different part of the bed, but I didn't know where, which specimen was printed where. So I had somehow to do some clustering of the data. But how do you cluster it? Essentially this? I can do it by, I don't know, I was really confused about how to do the clusterization. But after I essentially realized, okay, I can apply essentially the same thing. I can apply the spline generation, and I can try to cluster the spline themselves, because the spline essentially carry the information about the structure. So if I, for example, compare each spline associated with each struct to all the others, and as metrics, I use the soft DTW. Is like an Euclidean distance, but it's for sequence. So essentially, even if you have some curve that it's okay, it's the same curve, but it's shifted. So for example, if you have a sine wave and you have another sine wave that is shifted of only a small period, the soft DTV loss function gives you a very small value because it sees that your two sequences are similar between each other. So if I use that loss function to somehow compare each specimen to each other, I see that a lot of specimens are similar to each other, but I see those very bad yellow band. So essentially, there is two or more clusters inside the data, and that's a problem because I don't know how to classify them. So what I've tried, I try to apply a very simple clustering algorithms such as k-means, that now you know how they work. So they just find you the sinusoids to minimize the distance that you're using. But by using k-means, I had some very nice cluster because those three are very nice, but I have a really, really, really bad cluster. So and this was the best clustering that I have achieved with k-means. So it didn't work. But remembering that I'm using that kind of neural networks to generate the new topology, technically that neural networks, that architecture can encode my sequence information into a meaningful latent space. that in the other case was used to generate the new struct, but in this case can be used to classify those structs. And by imposing that each cluster should have a Gaussian distribution, because I mean, I will expect this kind of distribution to appear in the cluster. I can train my neural networks to do the classification, and I have those much nicer cluster. I mean, of course, with clustering, you can generate ideally n cluster with n your number of data. So each cluster is 1 point, but what's the point on doing that? So I am expecting some situation by this. So with some distant specimen inside the cluster, but that's a lot better respect to the previous scenario. And by clustering data, I was able to augment data, because here I had not very much data to do the struct generation. So how do I augment data in this case? With image, you can rotate them, you can mirror them, you can apply some filter, you can change the color, you can do a lot of things with images, but with sequence, not very much. You can try to divide the sequence into small subsequence, but that's not really generating new data. You are just sampling data in a different way. So I used something that it's a problem with neural networks, but in this case, it is something good, because when you feed an online neural networks new data, it tends to forget old data. So in this case, I augmented data by not doing a statistical generation, but using a statistical generation of an FFT transformed sequence. So essentially, I deconvoluted between trend, between seasonality, and I've retro-transformed the data after sampling inside those distribution, and I've generated those fake data, and I pre-trained my neural networks on those fake data. And after a while, I just fed the neural networks the real data with the assumption that after a while, it would forget the initial data. But that's really useful, because with a lot of data, of initial data, the neural network itself was capable of achieving a very optimized state, so a very stable numerical state. So that's for data augmentation. Now I have a very, very big problem, because my neural networks is huge. Technically, it can be very, very large. So as you have seen before, each neural network has a lot of hyperparameters that can be chosen. The width of neurons, the number of layer, the kind of activation function. You can have a receiver connection between each layer. You can have different kind of situation. And moreover, in this case, the connection inside the CFC layer, you have to specify what kind of connection you want inside of it. The research space is huge. Is even much bigger if you consider that you have also to optimize your training. And neural networks are very susceptible to hyperparameters initialization. Your networks can also not converge at all. So that's a real problem. You have to optimize somehow your neural networks. You could do, technically, a grid search. It's a really simple algorithm. You just divide your hyperparameters into intervals, and you try all of them, and you pick the best one. But it's infeasible when you have that much parameters, because you have an n per n per n per n search space. You can use a Bayesian optimization, but when the search space is too big, and in this case it has some categorical values, it collapses into a random search, so you are not really optimizing the structure. But you can use a genetic optimization. that is very, very fast, and it is very, very stable. But what is a genetic algorithm? A genetic algorithm is something that is inspired to nature, to how we evolved. So you have to encode your search space, your task, into a genome. You have to create genes, you have to create chromosome, you have to create the genome of the individuals. So in this case, I encoded the information of each layer into a gene. With enough genes, I've created some chromosomes, for example, related to the encoder, some chromosomes related to the decoder, some chromosomes related to the training process. And those chromosomes created the genome of an individual. I initialized a population of individuals with the values of each genes chosen randomly between two intervals, of course. And I let the population evolve. But how do I compute the fitness of this population? Because of course here just the fittest individuals can mate and can reproduce and can carry on their genetic information to the next generation. The fitness here was just the accuracy of the model. So it's very simple. And this kind of approach is very parallelizable because each life of each individual can be run independently in parallel. So if you have access to an HPC cluster, you can run all of these things simultaneously. Okay? So you let the population evolve. At each generation they mate, there is some crossover, some mutation, some inversion, a lot of genetic operation that you can customize, you can create. I created the library from scratch, so I could add basically everything. And this is the genetic evolution. You can see here the structure of the encoder and the decoder evolving. As you can see, at first it expanded. But since I added some tiebreaker parameters, so I said, okay, give me the best individuals, but also penalize a little bit architecture that have a big structure. At the end of it, I'll just replay it. At the end of it, it optimized the neural networks to be very small. So despite it being so small, it's so optimized to generating struct. And as you can see here, it's a very narrow line. I couldn't change that, sorry. But as you can see here, there is a constant optimization of the performance of the model until you reach the end of the generation. And those are the predicted, the generated struct. This is the real, this is the AI generated. They are essentially the same, and you couldn't tell the difference. And just for reference, that was the statistical generation. And you can see the huge gap into the two different generations. So that's the end of this work. So now the pipeline works. So essentially, you can attach those structures to the lattice itself. So that's for the second research. Now, I have time. Now I will finish a little bit sooner than I expected. But now the last part is the modeling and optimization of the static mechanical properties of a FDM specimen. Why FDM specimen? Because as I said before, the dominium doesn't really matter. So if this thing works with FDM, it works also with a SLM. And if it works with the mechanical properties, it can work also on fatigue, okay? So I use FDM and static mechanical properties because it's cheap and it's fast. So to develop a pipeline, it's very easy to do that, and I could afford that since a lot of filament I have to about it for myself. So I will skip this part because you know a lot about it. But just a quick recap because we hadn't talked about it. Decision tree. Decision tree are one kind of machine learning algorithm. I will explain them in a different way, but I think it can give you a different point of view. With decision tree, you are trying to maximize the decrease in entropy of your when doing classification in your ensemble. For example, you have a lot of animals. You have all the animals on the earth, and you are trying somehow to classify them. And you have to choose how to split your animals. So, for example, if you say, okay, I split the animals in the animals that are on land and the animals that are on water, I have maximized the decrease in entropy, because now I've essentially just classified all the marine life. Okay, so essentially what it is what the decision trees does. And that's what just one decision tree, but you can combine more decision trees to form a forest. But why that? Because a decision tree couldn't be really good at predicting your thing, but if you add an ensemble of trees, maybe your prediction will get better, okay? Because you can combine the prediction of all the trees. But a lot of times, those kind of ensemble algorithm and doesn't work when the domain is too complex. But a much more powerful tool is XGBoost, and it's similar to AdaBoost. So it model essentially the misprediction of the previous model. So you create an model, not ensemble, but a boosting model. So each model fixes the error of the previous model. And that is really simple, but it works really well. And it's behind also the discovery of the Higgs boson. So if you want to check it about it, but it's a really nice story. It helps a lot the classification of the Higgs presence into the spectra. So they use also XGBoost to find those peaks. But now into our problem, we have to somehow learn the relationship between print parameters and the mechanical properties. But why that? Because in additive manufacturing, and FDM is one of the kind of manufacturing that you can have, you have this kind of structure of your pipeline. You start with the design, we follow with the manufacturing of your specimen, you test your specimen, and after you have tested enough your specimen, you can start creating some model. And using the model and some practical consideration, you can modify the design, you can modify, of course, the manufacturing parameters, and you continue this cycle until you are satisfied with your mechanical properties, essentially. But this cycle is costly and is very, very, very time-consuming. And for example, in FDM, the mechanical properties are very susceptible to very small variation into the manufacturing parameter. For example, it can appear out of nowhere micro defects, but much worse, it can appear micro defects as a micro voids, under extrusion and over extrusion, and they can affect heavily the mechanical properties. For example, the toughness or the strain at break of your materials, and that's a problem also for fatigue. Okay? So the problem here is the modeling. Just one moment, I will drink a little bit of water. So the problem here is the modeling solution, because the model is the weak link of all of that. So pasta process tried to apply something like regression planes. They are not really planes. They're much more hyperplanes, but basically they try to treat each print parameters as an independent parameters. So without correlation, without interaction between each parameter, and of course they don't work. Parameters interact during a print. For example, in SLM, I'm talking about the LSM because I think here a lot of people work with metal. So of course, laser speed and the power of laser are correlated. They have a relation with each other towards the final mechanical properties. Okay, so that doesn't work. You can try also with the regression surface. They can technically take into account interaction between parameters, but they scale very poorly with a number of dimensions, because to build a very good regression surface, you need a very good data scientist, and since you have to somehow learn the interaction between parameters. And it's okay if you have 3, 4 parameters, but if you have 25, like in this case, it's pretty much impossible. So another another alternative was to use AI or machine learning, because they are very good to predict stuff. But in the past, they have only been applied to small domains. And that was a problem, because for both SLM and FDM, it wasn't basically an understanding of the process. So we wanted to vary and take into account all the process parameters of the FDM print process. And all the interval that those parameters could assume. And we just stopped at the values that our machine was capable of. So from the theoretical minimum to the theoretical maximum, okay? And that's something unprecedented. But since now the domain is so much complex, we have to increase also the power of our model. So we use an handheld statistical boosting neural networks. So I'll split into a small bit to make you understand better. So an handheld, since here we are trying to model n mechanical properties. So we have one head for each mechanical properties, okay? So we have a specialized model for each kind of properties that we want to model, because maybe some properties is more difficult than another one, so we need different neural networks to accurately model each one of them. It's statistical because additive manufacturing is a partially observed problem. We don't see everything. So if you use the same print parameters to manufacture something and we test it, we see some variance. That's pretty basic. That's why we do batch of a specimen and we test batch of things, because we are interested in the mean and the variance of our specimen. So neural networks shouldn't give a deterministic prediction. It should give a statistical prediction, because that's what we observe in reality. So the output must be a statistical distribution, okay? So it's boosting, because as in XGBoost here, we have n model that model the error of the previous model. So that increased the accuracy by a lot. Now, all this thing is completely automated. It doesn't exist a library. I just coded myself. So it just do this automatically by pushing things into cluster, retrieving information. But I'm planning for the future to create something that is useful also for people that are not that much into programming. But either way, that's just for the modeling. I also have to add information about my dominium to increase the accuracy. For example, here I'm talking about polymers, but it could be extended also for metals, but with different parameters, of course. But since here we are talking about polymers, I had to add also the thermal fingerprint of the polymer, information on the mechanics of the polymer themselves, and the information in this case about delamination, because in FDM we have a problem with delamination of layers. Okay, so by adding those information, the network itself improved a lot. Now the research branches into two. One used just deep neural networks. Another one, and that's this one, used a mixed approach. So something that has a little bit of neural networks and a little bit of classical machine learning. So in this case, since I added a lot of information as input data, I have passed from 25 dimensions to 75. So I have a huge increase in dimensionality, and that's a problem. So I had to encode or somehow compress information into something smaller. I could use a principal component analysis, but in this case, I had not redundancies into my data. So if I use that, I essentially lose information, and I can't afford that. So I trained an autoencoder, a variational autoencoder, and I just took the encoder after training. So essentially, since the autoencoder is good at doing x is equal to x if the latent space is smaller than the input space, I'm essentially encoding information in a very meaningful latent space, since this latent space is decoded into something that is equal to the input. So the latent space must be meaningful, okay? So that's for the encoding. I use XGBoost as the main component of the model, and now XGBoost can also model the statistical distribution. So essentially, I just made it model the mean and the variance of the statistical distribution associated with the prediction, and I optimized the negative log likelihood of the prediction. So that's the comparison with standard XGBoost. I have to contextualize a little bit the data. The orange line is it should be the perfect prediction, and the blue dot is the prediction. And as you can see, the XGBoost perform very poorly because it basically doesn't predict really well the data. But again, we have a lot of data, a lot of dimensions, sorry, in this problem. The data is sparse, and the data points are not so much, because maybe they was maybe in the order of 300. They are not really that much. By employing our architecture, the prediction somehow improved a little bit, but honestly, they are not satisfying really much. Here we can see that they improved compared to XGBoost, but the improvement isn't really that remarkable, honestly. So we have used something more elegant into our architecture. Something that it could be called physically informed neural networks. Now it is so much on trend, calling everything physically informed neural networks, but this isn't really a physically informed neural network. It's a domain informed neural networks. So we have extracted some mechanical information about our polymers. For example, in FDM, we just printed some specimen with all the infill line oriented with an angle, and an angle that is perpendicular to the first angle. And we tested those specimens. So those was the mechanical information that we gave you, the neural networks as an input. We essentially use those mechanical information as baseline. Okay, so XGBoost now had to just compute the coefficient. Okay, that once multiplied to the additional information and summed, they should give you the final mechanical properties. Of course, we have also thought about some residual information that the neural networks could also predict if the mechanical properties were outside the additional information that we have extracted. But essentially now the problem, it has become a lot simpler, because now the model, it has some domain information. Okay, so the optimization process itself should be a lot easier, but that's just for one of the model, one of the XGBoost model. Since XGBoost is technically just one model, and the N model that the model, the misprediction of the previous one, I had added N XGBoost model. So now XGBoost is also an ensemble model, and there is a neural networks behind it that it computes the weight of each model based on the position of the input data. And those are the prediction. Here on the bottom, those are the prediction. And they're really, really good. You see, there is, I mean, when we are dealing with additive manufacturing, you won't see a perfect relationship between predicted and real, since also real have a distribution. So something like this is very good. It's very, very good, because it's the confidence region always touch the real observation. So this is the real dynamic of the process. For example, those 5 points, those were a batch so this is the variation of the batch itself. And you can see that the confidence of interval always touches the predicted the observation. Sorry. So here it's the metric. As you can see, it's the accuracy increased by double compared to the previous model, and it is increased about 500% compared to the standard XGBoost. So as simple as that, we have changed really a small thing, but as you can see, if you somehow type the information better in your neural networks, your metrics, your accuracy will improve a lot. So we have now a nice model. We can predict things. That's nice, but we have a nice toy in our hands. We just need a method on how to exploit that model. And for example, one of the methods that we can employ is something that it will explain the black box, because in our case, our neural networks is something really complex, and we cannot really understand by looking into the coefficient what is really the dynamics of the process. So we can use some mathematical tools. For example, the Shapley values. They are based on the game theory. I will not get into depth about this expression, but they just play a game where one value is fixed. They make vary another value, and by doing that, they learn the marginal contribution of each parameter. So essentially, you have at the end of this process, you will have a grasp on how varying one parameters affects your prediction. So in this case, how varying print parameters will affect the final mechanical properties of your specimen. And here it is the complete Shapley values for rigidity. I don't know why, but it's very blurred. I don't know, maybe it's the projector, but for the rigidity and for the toughness. And for example, we can see here, I mean, in this case, the train data was just nylon, carbon fiber nylon, but the polymer itself was nylon 6.6 and nylon 12. And we can see that for rigidity, it is increased for very low layer rate, for very high solid field, so solid field speed. So maybe here by speeding up the printhead, the chain themselves were stretched. So somehow that increased the crystallization inside the polymer. So it changed the macrostructure inside the polymer. Of course, you have to somehow give you an explanation to those numerical values. But as a material scientist, you can do that. And you can do that here with polymers, but you can do it also with metals. And of course, here, by increasing the temperature of the heat bed of the print head, it is increased the adhesion, and so it is increased also the rigidity. And essentially, the same thing happens for the toughness, but it's different here. Here, for high layer height, we have a high toughness, and for very small values of acceleration, of speed, and of jerk. The jerk is essentially something related to the derivative of the acceleration. So here we see, of course, that the toughness increase if we somehow lowers the instances of defects, because with a thicker layer rate, I have fewer interfaces, so I have fewer defects inside the specimen, and by slowing down, there are less defects in my materials. So that makes it's completely fine. It makes sense, this explanation. So that's for XGBoost. Now I've tried to apply the same thing, so to the same data, a different partition of the data, because I have a lot of data of FDM specimen, but in this case it's just PLA. But in this case it's just a deep neural network. So as before, the autoencoder, so the encoder to compress information, the multi-layer perception as main architecture, and in this case, the structure of the multi-layer perception is bio-inspired, because as I said before, on the beginning, multi-layer perception can be very easily customized. So you can change their structure very easily. And in this case, in the depth of the multi-layer perception, I've changed the hidden size to mimic the compression and the expansion regions that are typical of human brains, humans and primates brains. So essentially, that created n latent space, so n compression inside the neural networks, and that increased a lot the accuracy. That's the slide broke a little bit. I don't know why. Sorry about it. But that is the prediction of the neural networks. And as you can see, those are very nice. Here on toughness, there were some problems, but it is not related for the neural networks, but it is related for the observation themselves. And in few slides, I will explain why. And just as a preview, this is how it changed the prediction. Those are the same predictions, but this is how it changed when I fed the neural networks the whole data that I have. I've stressed trained this neural network on a very small partition of data, because I wanted to see how to maximize the accuracy even with a very, very few input data. But if I train the neural network with all the data sets, you can see here how the prediction improves, and improves by a lot. Okay. So another thing that you can do with a Shapley value, in this case, only for PLA, because for nylon it was not the case, but we have seen that the parameters weren't nearly interacting as we expected. So we could force to the neural networks some not interaction. So basically, we applied a kernel to the neural networks itself, truncated Taylor expansion kernel. So essentially, each neural networks just compute the coefficient of the truncated expression of the Taylor series plus the residuals, and everything works as before. But in the end, we have an increase in accuracy respect to the standard model. So that was just to show you that by using sharp value, by using some logic to increase, to give more context to your model, you can increase its accuracy. Okay, so that was just to, and this is of course the comparison between XGBoost. You have to look at the blue rectangle, because those are the test partition. Okay, so you can see the increase in accuracy, and it's dramatic. It's almost the double of it. Okay. And as for sharp value, in this case, we have a different scenario, because PLA is a thermosensitive material. So here relationships are different. For example, here we see that rigidity is decreasing for high value of temperature. But why is that? Because PLA is thermosensitive. So if I increase temperature, I am degrading the material. Okay, and this is also true for the chamber temperature. If I increase too much the chamber temperature, I cause the polymer to be hot for longer times. So I need to quench the polymer in this case. I see something also very, very peculiar, and this is really peculiar for toughness, because I see that contrary with other case, it is increasing for a lower layer rates, it is increasing for high jerk and for high acceleration. So essentially it's completely the opposite, but this is strange. The presentation broke, I don't know why. It is really broken here. Can I adjust, because that is kind of important. So, I mean, I will talk, but that's unfortunate. I don't know why, because it was working on my PC. So I mean, I'll try. So there is somehow a toughening effect induced by the extrusion, by the high flow of the extrusion. So if we see, for example, the DSC of the tested specimen, of the high toughness tested specimen, we see that in the untested, we have a very strong enthalpic release. And this enthalpic release is associated with the formation of a meta-stable semi-crystalline structure that it was only possible by the high flow condition during the printing process. So essentially, due to the high shear stress inside the nozzle, the polymeric chain oriented themselves into that metastable structure, and since the layer is so thin, that quenched very fastly, and it became frozen in time, and it survives upon testing. And you can see here that after testing, the enthalpic release increased. So I've also increased the number of semi-crystalline structure, but it also increased the peak of melting. So if I compute the crystallinity at the end of it, I see that the tested specimen, it is a lot more crystalline than the printed one. So those crystallization absorb energy, and this is, for reference, the curves that of the high tough PLA that I'm talking about. And this is the point where normally PLA breaks. Okay, here where it breaks normally, and here where it broke. Okay, so that's the toughening effect of the print. And this analysis was possible since we have built on neural networks, and since we have performed the SHAP analysis on the neural networks, okay? Because otherwise, we hadn't seen that relationship between input parameters and mechanical properties. So I will end the presentation with some nice application. Because I've said at the beginning of the presentation that this was the modeling, but also the optimization of the mechanical properties. So we now have a model that we have validated that is real, because it reflects something that is really happening into the specimen. We have validated through reasoning, we have validated through data, so it works. Now I can apply something like a reinforcement learning algorithm or a genetic algorithm to somehow exploit that model as a virtual environment to optimize the print parameters to have a target mechanical behavior. Okay, I can use a reinforcement learning, I can use genetic algorithm. In this case, I will show you the genetic algorithm pipeline, because the reinforcement learning is very big and I've not that much time. So about the genetic algorithm, I've explained it before, so you know how it works. But in this case, the blocks, the gene inside the individuals are the print parameters. So each chromosome, it has different gene associated and different print parameters clustered by me based on similarity. For example, all the movement parameters, or the structural parameters, or the position parameters, all the test parameters, okay? And I let the optimization go. But in this case, I had to do some changes, because here we are maybe interested into doing a multi-objective optimization. So we want to optimize multiple mechanical properties at the same time. So I've used a non-sorting dominated genetic algorithm, the third version. Sorry, here it's written 2, but after I applied the third version of it. So it essentially can optimize at the same time multiple objectives. And that's really nice. And here, it is the prediction of the is the output of the optimization algorithm. So here I was asking the neural network itself to maximizing the yield stress and minimizing the density of the specimen. Of course, those two objectives go against each other. So I kind of expected this kind of output. So I have the Pareto optimality frontier here. So I can choose the point based on my use case scenario. For example, I want 50% of density higher, or I want this kind of stress field. I can choose. Those are the optimal parameters for this given task. And just to be complete about it, the neural network itself has been fine-tuned by applying a physics-informed neural network logic. Because in this case, each head, it has basically trained without any constraint, any mathematical constraint. So technically, due to some numerical instabilities, we could have some numbers of the input parameters that give you unrealistic results. For example, a yield stress bigger than an ultimate tensile stress. Of course, that's not possible, but technically it can happen due to mathematical instability. So with a fine-tuning that it applied a soft constraint, okay, with some self-weighting loss function, we were able to eliminate completely the mathematical artifacts. Okay, that's just for saying. And those are the specimen manufactured with a hand. And now one thing very, very nice that it emerged at the end of all this framework, and it honestly it was a little bit of a surprise, because at the end of the optimization algorithm that I've shown you before, I mean, the optimization process was constrained on using only PLA reinforced with a wood fiber and with flux fiber. I was just honestly toying with the algorithm. But I've noticed that it was giving me a lot more, because this is scaled, but they are not on scale. If I have shown you the real frequency, the blue one would be flat, okay? So the algorithm was proposing me a lot more instances of PLA reinforced with a flux respect than PLA reinforced with a wood. And also the signal associated with the stress field was a lot higher in the PLA reinforced with a flux than in PLA reinforced with wood. And in composite materials, the yield stress is a proxy value for the interface strength between polymer or between matrix and reinforcement. So basically, the model and the genetic algorithm was they were finding that PLA with wood, it wasn't having any interface between matrix and fiber. And it was finding that just by looking at the data. To confirm that hypothesis, we conducted some SEM analysis on the fracture surface of the specimen, and we have seen that it is indeed present an interface between the flux and the PLA, and it is absent an interface between wood particles and PLA matrix. And mind that the PLA is the same. There are no additives. It's the same matrix. So here, just by looking at the data, the model itself was able to learn that without any prior knowledge about all this stuff. So what I want to say is that the combined use of those mathematical tools can also help researchers to better analyze the behavior of materials. Of course, you have to know what you're looking to. Okay, so that's all. This is the software that I have used into all my works. I work with Python and with PyTorch. There is a reason behind it, because technically Python, if you use NumPy, and PyTorch, they could compile in C++. So you don't have to know how to code C++, because I mean, it's not for everyone, but Python is very easy to use. And you will have the speed up of the C++ code, if you code properly, of course. For hyperparameter tunings, I use WAND-B. It stands for weight and biases. It's an open library. It's free, and it can help you with cloud services for optimization. Of course, it doesn't give you any computational power. It just helps you for the optimization search, and it offers some very nice cloud capabilities that you can use for clustering your work into different machines. And those are the courses that I will honestly advise you to follow if you want to learn a little bit more about machine learning. They are all free. On Coursera, you can find a lot of free deep learning courses. They are all free. Sometimes they are not really great for explaining really how that stuff works, but if you follow them enough, you learn how AI works. Of course, you have to apply it to fully grasp how things work. Also, here on edX, this is a really nice introduction to computer science. If you don't know anything about programming, follow that first, because that's really nice, honestly. And as for environment, I use Visual Studio Code to code, and I really suggest you to use it if you want to code MATLAB or anything. And that's my email if you have any question. Thank you.